Chapter 6, Section 1, Part 2. We're picking up with exponential growth and decay forms. Just to review, the basic exponential is y equals b to the x, which comes from y equals a b to the x, where a is your starting amount, b is your rate of change, and x is how long. Okay. We also talked about y equals a times 1 plus r to the t, and y equals a times 1 minus r to the t. Basically, you're replacing the b with 1 plus r, 1 minus r. So your rate, percentage expressed as a decimal, added to 1 is going to be bigger than 1, so it'd be growth. Or your rate expressed as a decimal and subtracted from 1 is going to be less than 1, greater than 0, so it would be decay. So we're going to look at rewriting exponential functions so that we can figure out what their rate is. The amount y in grams of the radioactive isotope chromium-51 remaining after t days is y equals a times 0.5 t to the 28th. To the t divided by 28, where a is the initial amount in grams. What percent of the chromium-51 decays each day? So we need to find r. What does r equal? That's the question. Well, that means we have to get t all by itself up in the exponent spot, and then we can figure out that 1 plus r, 1 minus r. We do know that this is radioactive decay, so it's going down. It's going to be a 1 minus r situation. We just need to figure out what the b actually is. So if we've got y equals a times 0.5 t divided by 28, remember we could write that as y equals a times 0.5 to the 1/28th to the t. We can separate the numerator and the denominator. Now we just take the 1/28th of 0.05. So let's try that out. 0.5. So 0.5 to the 1 divided by 28. Nope, there's supposed to be a divide in there. Okay, so we get y equals a times 0.96 approximately, we got to switch to the squiggle, to the t. Okay. Now, I guess in your book, I just looked over at my book here real quick, they did 9755. They went to 4 decimal places. It doesn't say go 4 decimal places, but, it would have been 98 anyway, but 9755 to the t. So we have to figure out how much 0.9755 is as a decay rate. So we need the r part of it. So we're going to take 0.9755 and set it equal to 1 minus r. Okay. Add the r over. R plus 0.9755 equals 1. Subtract 0.9755 or find the difference of 0.9755 and 1. So r, and we are going to be squiggly now because I approximated, because that decimal is irrational, goes on forever. So let's see. Let's take 1 minus that. If I could come back over here, minus 1 minus. So we got 0.02445. If I go 4 decimal places like they did in the book, it'd be 0.0245. 0.0245. So expressed as a percentage is 2.45%. Okay? That's how much it decays each day. So whenever we get these that have these fractional exponents, we want to get t by itself, so separate off the denominator and any other numerator that is not just t, and then take that base number to that exponent and get your new b. That will be your decay rate, and then you can figure out what your rate of decay is from 1 there. So we talked about exponential growth and decay, and this is kind of how loans like to grow. You buy a car, you buy a house, do all that kind of stuff. You have a bank account, savings account. They will grow with exponential amounts because every amount adds to the amount next to it that was previous. The best kind that you can get is called compound interest. It's the best to get whenever you are investing and saving money and trying to grow it. It is the worst whenever you are borrowing or loaning, like a credit card. Those kind of things. They're compounding interest all of the time, all day, every day. But there's a formula for it, okay? So compound interest is interest paid on an initial investment called the principal and on previously earned interest. So the way that this compounds is they're not figuring your interest, or they're not figuring out the extra amount based on the original only. It's the original and whatever just added, and then whatever just added, and then whatever just added, and then just whatever. So as your thing grows, your interest grows. It's not the same amount every time. This is called compound interest. Okay? It's often expressed as an annual percent, but the interest is usually compounded more than once per year. So the exponential growth model, y equals a times 1 plus r to the t, must be modified for compound interest problems. So consider the principal. This is important. Principal is the start. Okay? It's an interest rate, annual interest rate r expressed as a decimal, n times per year. Big A is the amount in the account after T years is given. Okay? So this is your final amount. This is your starting amount. This is your percent rate as a decimal. This is how many times. And then T is years, right? And how many times happens twice? Because it's stuck inside itself. This is very similar to y equals a times 1 plus r to the t. But if you'll notice, the r is now divided by n and the t is now times n. But big P and little a were the same number. Y and big A are the same number. But the compounding adds that n, how many times is it compounded aspect to it. So it could be compounded 12 times a year or monthly. It could be compounded 52 times a year or weekly. It could be compounded 365 times a year, daily. And there's another one called compounded continuously that we'll get in the next lesson. Okay, so find the balance in an account. Don't forget, we got A equals P times 1 plus R divided by N to the NT. That's our equation. You deposit $9,000 in an account. This is our start. This is big P. That pays our R, which is actually 0.0146 as a decimal. Find the balance after 3 years. That's my T. When the interest is compounded quarterly. Quarters. There's 4 quarters in a dollar, so that's 1/4 is my N. That's how often it's compounded. So big A equals 9,000. That's my P. Times 1 plus R 0.0146. Okay. Divided by 1/4 or 0.25 to the 1/4 times 3. Okay. That's my 1, that's my plus R over N, and that's my NT. Everybody's the same. And then all we have to do is plug her in. 9,000, those are decimal places. 9,000, parenthesis, 1 plus 0.0146 divided by 0.25, that's 1/4 is a decimal, to the 0.25 times, nope, I'm going to go back up there, to the parenthesis up there, 0.25 times 3, and we get $9,391.39. Do it to the hundreds because it's pennies. That's where pennies go. Right behind the 9 is a 0, so the 9 stays. 2 decimal places. So you stick in $9,000, and then 3 years later, you've got an extra almost $400 just for waiting and doing nothing with it. That's called investing. That's a little small yield savings account. And actually, that's a pretty good rate for a savings account. The highest ones are like 1.8% right now. If you can get it compounded different, that makes it a little bit better. All right, so here's a couple of examples from what we looked at today where you have to change the look of the equation so you can find out the b actually, and then doing more compounded interest. Try 7 and 8, give it a pause, come back. Okay, number 7. We've got radioactive decay, so we got y equals a times 0.5 to the t divided by 13. A is the emission amount in grams. What percent of iodine decays each hour? We know it decays, so it's going to be a 1 minus r situation. I'm going to change this into 0.5 to the 1/13th to the t. And I'm going to see what that is, 0.5 to the 1 divided by 13. So y equals a times 0.9481 to the t. 0.9481 equals 1 minus r. If I just do this, changes all of them, and then just add 1 over. So I want that plus -1. And I just do the opposite of that. So 0.0519 equals my approximate rate. I should have done approximately there. So if I move that over, R is about 5.19% is how that moves down, okay? I could have said up here, move that back over this way, do 1 minus that. There you go. That's where it looks right. Now let's try B, or 8, sorry, don't know why I called it B. In example 5, find the balance after 3 years when the interest is compounded daily. So let's go back and look at what we did before. We did 9,000, 0.0146, and we did 1/4 of the year because it's compounded quarterly. Daily, how many days are in a year? That's 365. So we got big A equals 9,000 times 1 plus 0. Go back to that rate again. 1.46%. So 0.146 divided by 365, and then it's 365 times 3. So let's plug that in. 9,000 times 1 plus 0.0146 divided by 365. Get out there. To the 365 times 3. So we get is about $9,402.95. So if it's compounded daily instead of every 3 months or quarterly, then you get $402.95. It's not a huge jump, but your percent rate is not a huge percent rate. You're only getting 1% each time they compound it. 1% is a very small amount of something, okay? But that's what you would get if you left it in there for 3 years. You get over $400. Okay, so looking at that equation, the basic one, y equals b to the x, y equals a b to the x, and then y equals a times 1 plus or minus r to the t. Plus is going to be growth, minus is going to be decay, and it gets even weirder when we compound it and we make it r over n to the nt. But you got to memorize all of that stuff, all of those equations, where what goes and what